Hello students, we are going to discuss test 12 today. The topic was Coulombs law and Gauss theorem. In the first question, it is given that 1 million electrons are added to a glass rod. So N is 1 million, that is 10 power 6. We want to find the total charge on the rod. The total charge can be given by Q is equals to Ne. Here electrons are added to the glass rod, so glass rod will be negatively charged, so Q will be minus of N is 10 power 6 and E is the charge on electron, that is 1.6 into 10 power minus 19, so Q will be minus of 1.6 into 10 power minus 13 coulomb. So option 2 is correct option. In question number 2, it is given that a body has charge of 9.6 into 10 power minus 20 coulomb. We have to check whether this charge is possible or not on any body. According to the property of charge, Q that is always quantized, that is Q is equals to Ne, where N is the integer number. We will find N for this charge. So N will be 9.6 into 10 power minus 20 divided by 1.6 into 10 power minus 19. This will give us answer N is equals to 0.6. Here N is equals to 0.6. That means we are removing 0.6 charge from the body, and that is not possible. So this charge is not possible on body. So option 2 is correct option. In question number 3, a force of 4 Newton is acting between two charges in air. Let's say two charges are Q1 and Q2 and they are separated by distance r. In air, force acting between them will be F is equals to 1 upon 4 pi epsilon naught Q1 Q2 upon r square. Now we want to find the force if space between them is completely filled with glass whose relative permittivity is 8. Let's say in this case force acting is F dash, that will be equal to 1 upon 4 pi epsilon naught epsilon r Q1 Q2 by r square. So we can write F dash is equals to, this whole term can be written as F divided by epsilon r. F is given as 4 Newton and epsilon r is 8, so F dash is 0.5 Newton. So option 4 is correct option. In question number 4, a charge capital Q is divided into two parts, Q1 and Q2, such that they experience maximum force of repulsion when they are separated by certain distance. Here, force of repulsion between two charges can be written as K Q1 Q2 upon r square. For given value of r, if we want maximum force of repulsion, the multiplication of Q1 Q2 should be maximum. It is possible in the case when Q1 is equals to Q2 is equals to Q by 2. We want to find the ratio of Q is to Q1 is to Q2. So Q is to Q by 2 is to Q by 2. This will give us the answer 2 is to 1 is to 1. So option 4 is correct option. In question number 5, two charges, let's say Q1 and Q2, each of value 1 microcoulomb, are at point P is 2I plus 3J plus K meter, and at point Q, that is I plus J minus K meter. We want to find the force between them. To find the force, we have to find the distance between them. So the vector R can be written as vector P minus vector Q, that is 2i minus I cap, plus 3j minus j 2j cap, and k minus of minus k, that will be plus 2k cap. So the magnitude of R will be under root 1 plus 4 plus 4, that is 3 meter. So force will be K Q1 Q2 upon R square. Value of K is 9 into 10 power 9. Q1 and Q2 both are 1 microcoulomb, so that will be 10 power minus 12 coulomb square divided by R square, that is 9. So force will be 10 power minus 3 Newton. If we convert this into dyne, we can write 10 power minus 3 into 10 power 5 dyne. So force will be 100 dyne. So option 4 is correct option. In question number 6, it is given that two charged particles of plus 200 microcoulomb and minus 200 microcoulomb are placed at the corners B and C of an equilateral triangle ABC. The side of triangle is 0.1 meter. We want to find the force on charge 5 microcoulomb placed at point A. First, we will give the direction of forces. Here this is positive charge and this is also positive charge. So between B and A there will be repulsive force. So direction of this force will be away from A. Let's say this force is F1. As 5 microcoulomb is positive charge and minus 200 coulomb negative, there will be attractive force between these two charges. So direction of force will be from A to C. Let's say this force is F2. We can clearly see the magnitude of charges are same and distance between them is also same. So we can write magnitude of F1 is equals to magnitude of F2, that is K into Q1 Q2, that is 200 into 5 into 10 power minus 6 divided by R square, that is 0.1 whole square. Now the angle between these two forces will be 120 degree. We can find the exterior angle. This is equilateral triangle. If this angle is 60 degree, this angle is also 60 degree, then this is exterior angle, that will be 120 degree. So we have two vectors having same magnitude F, and angle between them is 120 degree. So their resultant F net will also have same magnitude F, and it will be at the angle bisecting line. So F net will be same as F. Put the value of K, that is 9 into 10 power 9 into 200 into 5, that is 1000 into 10 power minus 12 divided by 1 by 10 whole square. So F net will be, this is 9 plus 3 10 power plus 12, and this is 10 power minus 12, it will get cancelled out. So 9 into 100, that is 900 Newton. So option 4 is correct option. In question number 7, the mass of electron is given, that is 9.1 into 10 power minus 31 kg. The electron is sent into an electric field. The intensity of electric field is 9.1 into 10 power 6 Newton per Coulomb. We want to find the acceleration produced. Here, due to electric field, the force will act on electron. The force is given as QE, and we can write F is equals to MA. So MA is equals to QE. So acceleration will be charge on electron is 1.6 into 10 power minus 19. Electric field is given 9.1 into 10 power 6 divided by mass of electron, that is 9.1 into 10 power minus 31 kg. Simplifying this, we'll get acceleration is equals to 1.6 into 10 power 18 meter per second square. So option 1 is correct option. In question number 8, 2 point charges having charge Q and minus 3Q are given. They are placed at some distance apart. Let's say distance between them is R. The electric field at the location of Q is E. We want to find the electric field at the location of minus 3Q. Let's say electric field at the location of minus 3Q is E dash. Here, the electric field at point Q will be due to the charge minus 3Q. As this charge is negative charge, the electric field of negative charge is always directed inwards. So the direction of electric field at Q will be to the right direction. Now electric field at point charge minus 3Q is due to charge Q. The direction of electric field due to positive charge is always directed radially outward. So electric field at minus 3Q will also be directed along right direction. So direction of E and E dash will be same. Now electric field at Q can be written as E is equals to KQ by R. Here charge is minus 3Q. We'll consider only magnitude. So K3Q divided by R square. And E dash is the electric field at minus 3Q due to point Q. So magnitude will be KQ divided by R square. Taking the ratio, E dash by E is equals to 1 by 3. So E dash is equals to E by 3. So option 3 is correct option. In question number 9, infinite number of charges, each of magnitude Q, are placed on x-axis at x is equals to 1, x is equals to 2, x is equals to 4, x is equals to 8, and so on. The value of charge is same, that is Q. We want to find the intensity of electric field at origin. Here, as all the charges are of same magnitude and same nature, the electric field due to them will be directly added. So electric field at x is equals to 0 due to this can be written as KQ by R square, that is KQ by 1 square plus KQ by 2 square 4 plus KQ by 4 square 16 and so on. So electric field can be written as KQ divided by into 1 plus 1 by 4 plus 1 by 16 plus 1 by 64 and so on. Here between two adjacent terms the ratio is common. 1 by 4 divided by 1 is 1 by 4. 1 by 16 divided by 1 by 4 is 1 by 4. So this is infinite GP, geometric progression. For infinite GP, this sum can be written as A divided by 1 minus R, where A is the first term, that is 1, divided by 1 minus R. R is the common ratio. Here common ratio is 1 by 4. Simplify this. this infinite sum will be result in 4 by 3. So we can write K is equals E is equals to KQ into 4 by 3. So E can be written as K can be written as 1 upon 4 pi epsilon naught into 4Q by 3. This 4 will get cancelled out. So Q divided by 3 pi epsilon naught. So option 1 is correct option. In question number 10, it is given that a uniformly charged thin spherical shell of radius r is carrying uniform surface charge density sigma. Sigma is the charge per unit area. The spherical shell is made of two hemispherical shells held together by pressing them with force F. So the spherical shell is made by joining two hemispherical shells and by pressing them with force F. We want to find on which quantities this force F depends. Here the pressure acting can be written as sigma square divided by 2 epsilon naught, but pressure is force upon area is equals to sigma square divided by 2 epsilon naught. So force is equals to sigma square into A divided by 2 epsilon naught. From this we can write F is directly proportional to sigma square area, that will be R square divided by epsilon naught. So option 1 is correct option. In question number 11, it is given that 4 into 10 power 20 electron volt energy is required to move a charge of 0.25 coulomb between 2 points. We want to find the potential difference between these 2 points. The work done to move charge between 2 points is W is equals to Q into V. We want to find the potential difference V, that is W by Q. Work done is 4 into 10 power 20, but we have to convert it in joule. So electron volt is converted into joule by multiplying it with 1.6 into 10 power minus 19 divided by charge. Charge is 0.25 coulomb. Simplify this, we will get V is equals to 256 volt. So option 1 is correct option. In question number 12, it is given that two electric charges of 9 microcoulomb and minus 3 microcoulomb are placed 0.16 meter apart. There are 2 points on A and B on the line joining the two charges at a distance 0.04 meter from minus 3 microcoulomb and in between the charges. Here point A is located in between the charges and it is at the distance of 0.04 meter from minus 3 microcoulomb charge. Another point B is out of the side of two charges and it is at the distance 0.08 from minus 3 coulomb charge. We want to find the potentials at A and B. Here potential at A will be due to these two charges and potential at B will also be due to these two charges. First we will write potential at A. Potential due to this 9 microcoulomb charge is K 9 into 10 power minus 6 divided by distance between them. If this is 0.04, then this will be 0.12. So VA will be K into 9 into 10 power minus 4 divided by 12. The potential due to this minus 3 microcoulomb charge will be K into charge, that is 3 into 10 power minus 6 divided by the distance, that is 0.04. So 3K into 10 power minus 4 divided by 4. This is 3 threes and 4 threes. So VA will be 3K into 10 power minus 4 divided by 4 minus 3K into 10 power minus 4 divided by 4. So potential at A will be 0. Now we want to find the potential at point B. Potential at B will be due to 9 microcoulomb and minus 3 microcoulomb. Potential at B due to 9 microcoulomb will be K 9 into 10 power minus 4 divided by distance between them will be 24 centimeter, minus potential at B due to this minus 3 coulomb charge will be, here minus sign is taken because this charge is negative, K 3 into 10 power minus 4 divided by the distance is 8. So VB will be 3K into 10 power minus 4 divided by 8 minus 3K into 10 power minus 4 divided by 8. So potential at B will be 0. Potential at A and B is 0. So option 2 is correct option. In question number 13, a positive charge Q is carried from point B to point A. In the electric field of a point charge plus Q, the permittivity of free space is given epsilon naught. We want to find the work done in this process. Here work done will be change in potential energy of charge Q. So work done will be final potential energy minus initial potential energy. Finally, the charge small q is at point A. So potential energy at point A can be written as KQQ divided by the distance A minus initially it was at B. So potential energy at B can be written as KQQ divided by B. K can be written as 1 upon 4 pi epsilon naught. So QQ by 4 pi epsilon naught into 1 by E minus 1 by B. This is the work done to move charge small q. So option 1 is correct option. In question number 14, it is given that two positive charges 12 microcoulomb and 10 microcoulomb are initially separated by distance 10 centimeter. We want to find the work done in bringing the two charges 4 centimeter closer. They are moved 4 centimeter closer. So in second case, the distance between them will be 6 centimeter. Here the work done can be written as change in potential energy. So work done is equals to final potential energy minus initial potential energy. Final potential energy in this case will be K Q1 Q2 divided by R, that final distance is 6 centimeter, minus K Q1 Q2 divided by R, initial distance was 10 centimeter. So K Q1 Q2 100 by 6 meter minus 100 by 10 meter. Value of K is 9 into 10 power 9. Q1 is 12 microcoulomb. Q2 is 10 microcoulomb. Take this 100 common. Divided by 2 into 1 by 3 minus 1 by 5. Simplify this, we'll get work done is equals to 7.2 joule. So option 1 is correct option. In question number 15, a square array of charged particles is shown. The distance between the adjacent particle is d. We want to find the electric potential at point P located at the center of square. The electric potential is 0 at infinity. Here from figure we can see that this plus phi q and minus phi q are located at same distance from point P. So potential at point P due to plus phi q and minus phi q will cancel out each other. Same way, thus minus 4q and plus 4q are also located at same distance from P. So they will also cancel out each other, and thus minus q and plus q will also cancel out each other. So potential at point P will be only due to this minus 2q charges. So potential at P can be written as K into charge, that is minus 2q, divided by distance. This distance is d, but this is due to both the charges, so we can say potential at P is 2 times of k minus 2q by d. So this will be minus 4q. K can be written as 1 upon 4 pi epsilon naught into d. So potential at P will be minus 4q divided by 4 pi epsilon naught d. So option 3 is correct option.